Okay, next up we have Dr. Bruno Xavier, who, as I mentioned earlier, is working at the Cornell Food Venture Center in Geneva, but he's actually going to talk to us about some of the work he did down in Brazil in using biochar in waste treatment. And if you could also just talk about anaerobic digestion.
Yes. Yeah, I put together some.
There's someone called Anne here who's waiting for a pizza.
Oh yeah, over here.
There you are.
Thanks, John.
So I just put together some slides here to show some of the points that were raised during the conversation that we had in the morning. Nothing very fancy, but at least will remind me to say a couple of things about this. So I graduated from Cornell as a PhD in microbiology in 2008. After my graduation was in food engineering. So I have kind of a mixed background there. But I've been working with solutions for waste management since my master's in Brazil. And so I usually look at approaches involving microbes in one way or another. What happened was after my PhD, we went back to Brazil, and I was in a very small university, small in terms of budget especially. Lots of students and engineering students from a very, let's say, challenging social background. So we had to be digging for scholarships for them all the time. And this is how this project started. A bunch of students asking for a possibility to create a project. How can we work together? So this is what we created. So it was, the group that we created is called BioSUS, Biotechnology for Sustainability, something like that. And biochar was the core of this. But if you can show me the next slide, this shows the idea that we came up with. So at the same time, 7 small towns were getting together to create a landfill that was to replace what each one of those towns had, which was just bad. And it's funny when you don't have good words to say something. And let's just leave it at that. and they asked us, okay, so do you want to have an input on this? And we came up with something that looked like this. So we looked at their budget and we tried to simplify as much as we could what the technologies that they could be used in there to reduce the cost that each town would have. So we would have the organic waste, the total waste in there. We proposed to them, do not introduce a recycling program that we divided into more than 2 categories. Just go with organic and inorganic waste. That would be the most efficient thing for them to do. What's not recyclable, okay, you will keep doing what you can in the recycling area here. And let's look at what can be recycled, what's inorganic. You're going to deal with that in your sanitary waste, whatever program that you have. But we want to deal with the organic solids and liquid that we have on the other side. So we came with the project that is on this side here, which would start with the pyrolysis reactor. We wanted to work on that with them and use the waste for that to produce some charcoal. The charcoal would be used in a biodigester, in a fixed bed bioreactor. You would produce methane, and we came with this idea that we wanted to convey at the time, is that using methane, purifying the methane that would be produced there to be used directly to generate electricity would not be feasible without a lot of investment, which they didn't have. So let's use that methane to power the pyrolysis reactor. And the syngas that would be produced there, then it would be easier for us to use as a source of energy to be produced in this way here. So that was the core of our technologies that we wanted to develop with them. Later on, that part up there was added because somebody, some politician really liked microalgae. That's one of the things, okay, we have to do something about, okay, microalgae. We can use microalgae there to produce biomass and biofuels there. Biofuels goes into bioenergy, and the biomass goes with the other residues into our pyrolysis reactor to produce more biochar. So we were not concerned, we were not at that level, we didn't have the technology to say much about the quality or the use of that biochar. We wanted to solve a very specific issue, was what to do with that organic matter that was going into a landfill of the worst quality that you could possibly imagine. It was right uphill from a river, just so that you have an idea. So we had a very important problem to solve. Another important branch here, which the biodigesters will solve, is the from the landfills, you have the water running off of that. So you have to, and that's a very bad residue because not only you have organic contamination, you have also lead, you have all kinds of metals. And we were playing with the hypothesis that our biodigesters, if we introduce several stages, we will be able to bind some of those metals in the early stage. Something like that, we would come up with a solution. But we knew that that was trouble. We needed to remove that from the waste. So the project with the landfills is coming, actually went online last year, and they do not have the pyrolysis reactor, but they do have some biodigesters working on this side of the problem. And we hope that in the future we will be able to develop a pyrolysis reactor that is big enough and will be able to accommodate their needs. There are some regulations. People still do not understand the difference between pyrolysis and burning. And how that affects the impact of such a technology will have on the environment. So we still consider this as a success in there. I wanted to say some things about what we learned during this process. First is that I truly believe that even though we're talking about carbon when we talked about biochar, that's what it is. I think the main thing that we have an immediate impact in the environment is not on carbon, it's on water. This area here is very dry. That's the next picture if you can, Morgan. The next one will be quick. This is just showing the biodigesters. I'll follow the slides. I think I'll cover everything if I follow the slides. Just showing some details about the biodigesters. What we did was to use a common concept here, and then we added some bags, basically bags of biochar inside the biodigester, and you could remove that over time. So we had, I think, 6 or 7 bags, and then 7 bags every day you would remove one. In that bag, after 7 days in the biodigester, was going to be dried and used as a fertilizer. I sent a sample of that material to a company in Brazil that made compost, and they said that they had never seen anything as good as that in their entire experience. So, and he was not my friend, but yeah, he came to the university as a professor too, in the same area where I was. So in that situation, you're not collaborators. In the academic world, we were competitors, unfortunately. And but anyways, so please next one, or Morgan. And this is the kind of solution that we had to come up with, and that was really fun, trying to come up with very cheap ways to measure gas production in a biodigester that had this is a lab scale version of it, but that was the first one we did. How do you measure methane when you don't have a gas chromatograph available? So we use this apparatus here. This will be, of course, the gas will be produced here. You can pump it in, and then the amount of gas here is basically, you have to use some equation to convert the amount because the pressure changes, but whatever. You know how much gas was produced, total gas. And then you can do several cycles of this through different solutions, and you precipitate different gases that are produced. You can precipitate CO2, you can assume that nitrogen is not produced, and so on and so forth, and then you come up with a number for methane. Well, I got to teach a lot of chemistry to my students that way, and got some decent results as well that were later validated with some decent equipment. But next slide, please. Like these. This is what Kathleen asked me to show you. This is shows the production of total gas. Okay, this is an early result in the biodigesters. These were I was treating a mix of manure, cow manure, cheese whey, and I added the biochar to it. In the beginning, we had one part of each, so a third of each in the final mix, and then after some amount of days, I don't remember, we would start adding cheese whey continuously to that mix. So what this shows is only a part of it, but this big line here is when we added the activated charcoal. And then you can go down. This is charcoal produced at 450 Celsius. This was produced at 300 Celsius, and that's the control without any charcoal. So we can see two things here. First, whenever we added any surface, any amount of charcoal, we increased both the time, reduced the time that it took for us to see methane in the biodigesters, and we also saw, and it doesn't show here, but the resiliency, that's how we defined it, but how trustworthy that methanogenesis was. Kaplan? Okay. And also, the bigger the surface area of that charcoal, the effect was more pronounced. We did not expect, actually, that the char that we produced, remember, with all that mixed, kitchen waste, basically, it was quite good compared to the activated carbon that we use, which is like the Ferrari of the carbons that we had available as the coconut shells. Very good stuff. But anyways, another thing is that you can see that this delay here led to another microbiology study that was fantastic, I thought, because it took longer for us to see a total production of gases in those biodigesters. And I confess that I was kind of upset. I was concerned about that. Like, charcoal is actually inhibiting gas production in the biodigester. But when we were able to look at what was being produced, we saw that these guys here were producing more gas, but it was basically CO2 from fermentation. What the charcoal does is that it binds the lactose from the whey and it slowly releases it into the water, where the microbes can have access to it and produce acid and CO2. But if the rate is right, the methanogens can use that acid to produce methane, and the pH is always stable. And the pH is key in these biodigesters because as soon as it goes down, the methanogens are the first ones to be inhibited, and then it's just an exponential increase in pH will happen because no one is there to eat the acids there are causing the drop in pH. So the charcoal had an amazing effect at stabilizing those biodigesters. It was one of a very good result that we had. Next one, please. Just some pictures so that you can see what we were dealing with. This is just to show how good the soil is there. Good. Yeah, awesome stuff. But yeah, we had, and this is just some trial that we did with anyone familiar with vetiver? I don't know how to say that in English.
Yeah, vetiver grass.
Yes, yeah, vetiver grass. And we couldn't grow that in this soil. But once we added char, what happens in that soil is that water filters through too quick. Char was biochar is low that enough so that the grass could grow. So we had some success using that as well. Next, please. Just some pictures now. We were even able to grow some samples to take this to events like these to show that we were able to grow beans in that soil. It is just regular black beans that no char, and then we increased the amount of char when we saw it, and they were left out so that this was just one example, but it was stuff that was grown, no irrigation, no nothing. To show that the char actually helped solving that issue. And again, the only difference is water in this case. Next one. We have a little bit of water. This is the pyrolysis reactor that we managed to create there. The objective was to replace at some point the propane with the methane from the biodigesters. They have done that since then with some success. I'm not sure how the results came out. But this is what we did, using a 50-gallon drum with another drum inside and a burner. So we start burning. Next slide we'll show that. But we start burning the propane, and at some point in the next slide, I think you can see that we recycle the syngas inside the burner through these pipes, and then it keeps going. So just by the time that the temperature starts to drop and then increase again, you can have an idea of what's going on inside the reactor. And we can do some mass balances to evaluate the success of the reaction as well. It's a lot of fun there. The results are not that reliable, but again, our main focus was to teach, and we did produce some good biochar. The first graph that I showed was produced in this machine here. The next one, please. Another thing that Kathleen asked me to talk about was microbial fuel cells. We also had a group having some MacGyver science. You remember MacGyver? MacGyver science on microbial fuel cell, and that was a challenge. Usually, they are made using glass and some acrylic sometimes, but basically a microbial fuel cell. Okay, let me backtrack here. Our cells, we need electricity to work. Our cells, in a way, they resemble a battery. So we need electricity and we need carbon. The electricity we need to produce ATP. The ATP we need to bind stuff together to make more cells. Microbial fuel cells come from that observation, and we want to take away some of that electricity from the cells, from the microbial cells, to generate electricity. We wanted to explore charcoal, as a replacement for the cathode in the microbial fuel cells. Next slide, please. Well, ideally we have them opposite, but anyways, each one of these chambers will be either the negative or the positive pole on that microbial battery, and we will fill them up with that Ferrari charcoal that I had there. Under $40 reais, so $50 per 50 kilos, whatever that costs you, but just so you know, it's pretty cheap in Brazil anyways. So, and we would connect all that thing together, next one, and we would, next again, it looks like that. We would have some ways to take samples and measure the electricity produced. Here you have a graphite electrode in the charcoal side, and then a platinum electrode on the other side. That's the only thing that would tolerate the difference in voltages. Next one. So with that, we were able to show that charcoal can be used in these microbial fuel cells, but nowhere, like everyone knows, you're not going to be able to produce electricity from it. But they are very good at as a way to reduce the amount of contamination in waste. I will show some results after I show all the pictures. So these are some experiments with microalgae that we did, isolating. We wanted to remove nitrogen from water using these microbes. So we were selecting microalgae that had a high affinity for nitrogen. So basically we were starving them for nothing but nitrogen. So the ones that could find nitrogen first were the ones to be selected. We had a collection of strains that were successful. We also studied some ways to separate the algae from the water using something called electroflocculation. But anyways, you can separate the algae, but then there was some consequence to that, not very good. But anyways, to produce the biomass that would go into the pyrolysis reactor in the future, just to satisfy some politician, but that was another history. Next one. So I keep going, please. Again, just showing that. I'm sorry, I didn't know that I was going to.
Should I go ahead and?
Yeah, please. Yeah. Okay, nothing useful here. Please, next. Okay, just shows the biofuel cell assembled, and a bunch of them being tested at the same time with the control. That's just a potential stack that provides the energy for the microbial fuel cells. And this is the kind of results that we got, that we wanted to show. The removal rate of carbon in different compounds here, but the most of the carbon in the sample was from acetate being produced by acidic bacteria in the whey, the cheese whey. A lot of acetate was produced, and the removal was greater when we had our bioreactors using charcoal as a cathode. It's not easy to interpret this data though, because we have carbon in the water and in the charcoal. In the charcoal, it's very hard for you to measure how much carbon was bound to it. But what we saw was that the effluent was cleaner, right? So it would take a long time for us to be able to come up with ways to evaluate this further. And there is good data produced showing how this happens. But we basically showed that we were able to reduce the leftover carbon in the water when we applied a differential of voltage to the different poles of that microbial fuel cells. Okay, next one. Again, when we had the carbon from the biochar, we had a more constant flow of electrons through the microbial fuel cell. It worked as a way to host the bacteria and deliver those electrons around our cell. Basically, was working as a battery. Next one. And we use different kinds of membranes to separate those two. That's not, you can flow through the next ones. Yep, and that was it. So it was a very interesting experience working with this. In the 6 years that we stayed there, I worked with 49 students, 3 graduate students and 46 engineering students. It was a very interesting experience. The main thing that I learned here was that water is basically where the first effect of carbon is. It comes back to what I was talking to Bill about the bottleneck that we should be looking at when we look at climate change. It might not be heat, it might not be because it's getting warmer, but it might be because we will not have enough water to grow our crops. And biochar definitely helps that in the short term. And you can see that by any small experiment that you set up at home. Also that an integrated 10 seconds. An integrated approach to make possible to small scale biochar-based systems actually work is not completely out of the realm of the possibilities here that could be used in large scale. So lots of small systems are also a possibility to solve all these questions of how to make the biochar system sustainable for our societies. Anyways, I tried to go as fast as I could, but if you have any questions, if you want to get together, now I'm working at the Food Venture Center at Cornell here in Geneva. Basically, if you want to make a jelly, a jam, and bring it up to market, please contact us, and we'll provide you with the documentation that you need. But thank you, and I'll be happy to take any questions. No questions.
I'm sorry.
Thank you.
My first question is there a Betsy still here? Because your pizza's ready. No, Betsy left early. Okay, does anybody want a white pizza that has meat? Okay, sorry, I didn't mean to cut you off, Bruno. I know there's so much information out there, and we're trying to squeeze a lot of different perspectives in.